I think you can come forward to sit so we can interact. Okay. So I think like we start the next part because although I had many things like on the first part, which is retrosynthetic analysis, how to how to make molecules. So I have instructed the students to post you up all the slides. So I have like I have bought many slides, but I think looking into the interest of time, I need to teach you the other portion what we have mentioned in the Gyan course, and that is something like the asymmetric synthesis and catalysis. I feel that this concept should also come up. So in the first class, I showed you that where we started, like how do we started organic synthesis, and where we are, and now at the present scenario, what type of sustainable synthesis we are thinking on. So organic chemistry is a pillar. So the pillars are reactions, stereochemistry, reagents, which are your toolboxes, and your understanding to approach a molecule through retrosynthetic analysis. With this, parallelly goes something very important, which is called asymmetric synthesis. And as we are discussing, that asymmetric synthesis means generation of new chiral centers. And in the last examples, you saw that what type of molecules you have. Lot of molecules with lot of chiral centers, and we need to think that how we need to make them, and also with high enantiomer selectivity. Okay. The other concept is catalysis. We are all familiar with this word because this is where we employ a small amount of a reagent in the reaction, which make it faster, which make it better yielding, and that's why asymmetric synthesis and catalysis should go together so that we can achieve 100% atom economy. What is atom economy? Atom economy means we should have any atom wastage. Who has coined it? Who has coined the term atom economy? Atom economy was coined in 1991 by Professor Barry M. Trost of Stanford. Okay, so is the first person who's coined the word, atom economy, and this is the place where catalysis was given a new name. Okay. Now, with coming on the introduction, of asymmetric, you are all familiar with all this, all these pictures which resemble chirality in nature and which are macroscopic, isn't it? You see the conch shells, the cacti picture I have given, the hands. Okay, I personally like all these pictures, the way they are kept, the sandals. I could not give, I feel the wrapping of a sari is also, something a chirality in nature, but I could not find a good picture. Golf sticks, hockey sticks kept in this way. These are all chirality in a macroscopic, way in the nature we find. So when we come to the microscopic level and chirality in nature, we can think of two things. One is, which is molecular, and the other thing is supramolecular, big molecules. Okay. So in the molecular side, we can think of amino acids, monosaccharides, alkaloids, and steroids in the natural products, which we feel resemble fantastic chiralities in nature. When we go for supramoleculars, we can think of protein, nucleic acids, carbohydrates, and lipids. Fine. Is chirality manifested in biology? Yes. So biology and chirality have a very strong connection. Like, we are two persons are doing a handshake like this. So both of them cannot exist without the other, what I feel. How? Is there any examples? There are a lot of examples, but chirality manifested in biology can be found when you think about an enzyme substrate recognition, how an enzyme works with substrates. Second is a drug receptor recognition, sense of taste, odor, pheromones, hormone receptor recognition. So all this are nothing but chirality mentioned in biology. Otherwise, there can be no existence of this type of interactions. Human beings would have been not called the living beings if this beautiful combination doesn't work, chirality and biology. Okay. The pheromones, olein, okay, it's a sex pheromone of the olive fly, and you see the pheromone is so beautifully chiral in nature, okay, and this is what I think the best resemblance of a pheromone, a chirality in biology. And if you see the mirror images, the left side mirror image is an isomer which attracts the males, okay, and the right side is a mirror image which attracts the females. So this is what is chirality in biology, okay. So we all know this, elements of molecular chirality in organic compounds. So, tetrahedral chiral carbon, we can have an axis, we all know, and you can have the rotations, keep rotating, there are mirror images, and we call it configurations or conformations also in some cases. We also have molecules where actually we don't find chiral centers, although the molecules are chiral, right? Like the biphenyls, like the allenes. This is a beautiful molecule, beautiful molecule. You can do a lot of good reactions, very nice stereochemical reactions. One of the best used molecules in industries now, believe me. There is one industry in Nagpur, just set up 2 years before. They are doing only chemistry with chiral allenes. And in the last 2 years, the industry has grown up like anything. So very beautiful. So we should learn. I am telling you about the toolboxes. A chemistry student is a powerful student when he knows the toolbox and he knows how to use the toolbox. So for a long time, people have not used these chiral allenes. That industry has started taking up these chiral allenes. They're making a lot of nice molecules. They have sent me a small, prospectus of their compounds just for their advertisement. I was going through very beautiful molecules. Okay. Not only this, one of the most useful, asymmetric ligands like binaps, that's just arises chirality because there is a steric hindrance across this bond, right? So what we call is R binap and S binap, very important ligands, very cheaply available, but fantastic enantioselective inductions. Planar chirality. What is this called? This might be a very known molecule to you. Ferrocenes, okay. Organometallics, okay. So what was the first organometallic compound which was awarded Nobel Prize? Do you remember? First organometallic compound which was, and the scientist who was awarded the Nobel Prize. Just keep your vocabulary on. Who was that? Who was Alfred Werner? He developed something called Werner complex. Okay. Okay. Now, if we just do some recalling of our existing knowledge, then you will find that the stereoisomers can be divided into two things. One is diastereomer and the other is enantiomer. So the diastereomers have different physical property. They are separable by chromatography or fractional distillation. And third is the NMR spectral pattern is different from each other. So when there are diastereomers, they have different physical properties. They can be separated when you do columns, and they will have different NMR patterns. Clear? When you come to enantiomer, they have identical physical properties. They interact only with plain polarized light, what we call as polarimeter. They have different optical rotations, and the NMR is also identical to each other. So these are also necessary because these properties help us to understand that after we do a reaction, we discussed a lot of how we approach a reaction, how we design a reaction. But what about when you get the product? We need to understand the product. We need to identify the product. We need to run to NMR. We need to see the NMR pattern and then say that, okay, this is our product. See, there are 3 steps. As a student, as a researcher, all of us have to maintain 3 things in our lab. The first thing is thinking about the reaction. I will never support a concept that you hurriedly set 10 reactions. No, you should have a complete overview like retrosynthetic analysis. You should think the reaction about 2 days before setting a reaction. Don't go and run and set 10 reactions. That's not going to work. The first thing is setting up the reaction, approaching the reaction that we discussed, how to approach the starting material, how to choose it. The second, I am continuously saying you, toolbox, which reagent you are going to use. The third is structural understanding of the compound or identifying the compound. I have seen large number of students that they have got the product in their hands, but because of not having proper knowledge on identifying the compound, they have not identified it. And if they have not identified the first compound, just understand that when you are planning multiple step sequences, if you miss one compound in your PhD or in your master studies, you are unable to do a bigger work. So first thing is the correct retrosynthetic analysis, second is the toolbox, and the third is identifying your product. This is also very necessary. You should not leave your compound until and unless you identify it. Sir, ये उल्टा सीधा कुछ हो गया है. This concept I have seen in our student is not correct. Even if you don't identify the product based on these characterizations, try to understand what has happened in your reaction. This is very, very necessary. Okay. Now, we need to understand what has happened, and we need to also understand when you talk about enantiomeric excess, particularly in asymmetric synthesis. Enantiomeric excess is a simple calculation, what I see, that which enantiomer is more in the mixture. This is what is asymmetric synthesis coming in, that you need to have a reaction which has to be stereoselective. So what is the difference between stereospecific and stereoselective? Stereospecific means that you have a substrate which keeps one enantiomer in excess. So it's substrate controlled. Your substrate is such a way designed that will end up with one product in major. That is what is stereospecific. And the other case is stereoselective, when there is a chance of equal opportunity of forming of two enantiomers, but you have one enantiomer in major. Okay, then which is more creditable? The more creditable is stereoselective. Why I say that? Because I have been approached with many people, even some experts. Sir, stereospecific तो बहुत अच्छा है, but stereo अच्छा है, but stereoselective से अच्छा नहीं है. So stereoselective is you design something where there is an equal opportunity of two enantiomers, but you generate one in major. So that attracts more credibility. Stereospecific is by default substrate controlled. Is that clear? So very nice, we cleared this concept. Okay. Now what is called chiral induction then? So chirality at center A influences the chirality at the center B in the same molecule. Closer the centers A and B are, greater is the extent of induction. And we find numerous prochiral groups. That means that these centers are actually prochirals. And if you have another group in the molecules which has a capability of generating a chiral center, we call it chiral induction. That chiral induction can be induced by any part of the molecule or a molecule coming from outside, what we call as chiral auxiliary or a ligand in local terms. Okay. So induction means you induce chirality actually. So that can be inside the molecule and that can be outside the molecule. I'll tell you, how do you understand? So you will see a common understanding among students that after running a chiral reaction, they run for HPLC. I have seen students. Why? HPLC is what? High pressure liquid chromatography, right? And ये machine क्या है? What is this machine? High pressure liquid chromatography. Funda is very simple. High pressure means there is someone who exerts huge pressure and the compound mixture passes through a column. So one side someone is pushing it, the compound mixture is passing through the column and going to the detector, and detector finds that okay, this is compound 1, this is compound 2, this is compound 3. This is way our HPLC works. Now the moment the chiral column, there is no difference. If the chiral column is packed with simple carbon C18 molecules, normal carbon molecules, they cannot identify chiral ones. They will identify different diastereomers. If the chiral packing is done by some chiral molecules, then it can understand that okay, this chiral molecule is passing through the column. And when it reaches the detector, it understands. But please try to understand HPLC. I have seen many students very confused about HPLC. There is nothing. There is someone who is injecting the molecules, molecule is passing through the column, reaching the detector. So एक तरफ से वो जा रहा है, pump खींच रहा है, detector पहुंच रहा है. The main science is in the column. I always tell my students that when you do the reaction, the main size is in TLC. TLC plate देखा है ना आप लोगों ने? TLC plate. So science is not anywhere. Science is in the TLC. If you can identify the product in the TLC, you are a better scientist. The moment the molecules pass through the HPLC column, so nothing is important in HPLC except the column. The column detects, and how does it detect? The packing inside. If it has a chiral Cephadex, it will identify every chiral molecule and it will reach the detector. So now the thing is that when you pass a reaction through such a chiral HPLC without knowing that is there any chiral induction, students go and pass it immediately. See, what you should do first, we have read that chiral molecules interact with plane polarized light. They deflect light, right? So what is your first duty? Your first duty is, if your reaction has a chiral induction, it should show a positive or negative optical rotation. There is no need of running to HPLC. Got it? So the first thing to understand as a chemist, that has there been a chiral induction in your system, can only be understood. Just do the reaction, take the vessel, take a dropper of the molecule, put it in the polarimeter, find it if there is a positive or a negative rotation. The moment you find it, fantastic, you have a chiral induction. So you have a pro-chiral substrate, you did a reaction, you got a chiral reaction. How to understand it? The best thing is passing the solution through a polarimeter, not running to HPLCs. Okay, very good. So in such cases, one diastereomer is selective, one is stereospecific, one is stereoselective. I have already explained. Okay, so these are some of the, I feel some of the important, manuscripts. I will feel some books which I would request you in your leisure time you can go through, particularly the Catalytic Asymmetric Synthesis by E. Ojima, and this is free in online and offlines. So please go whatever is available, any one article in your time which will increase your concepts regarding the asymmetric synthesis and catalysis. Anyone, all these are equally important. Asymmetric or organic reaction by Moser, even Professor Jacobson has written a fantastic article on comprehensive asymmetric synthesis. Catalytic asymmetry by Ojima, this is one of the most read articles, I feel. Very nicely written. It clears your concepts like anything. So please go through any of this which is available with you. Okay, now let me go to, okay. So this is what I started, and we think about asymmetric reactions. Just see this reaction. What is an LDA? LDA is lithium diisopropyl amide. How do you generate? You generate it very easily, right? Okay. Okay. So I write something before I go to the reaction. I've seen mentioning in the books that LDA. LDA is nothing but lithium diisopropylamide, and you will see in majority of the cases the book has mentioned minus 78 degrees centigrade for the reaction. So I'd like to tell you that this is just an exchange. You take diisopropylamide and put n beta lithium, and this exchange reaction is just an exchange of the hydrogen and the lithium ion, and this is what is lithium diisopropylamide, and this happens in minus 10 degrees centigrade. There is no need of doing the reaction of minus 78. If this exchange happens in minus 10, then why the books report minus 78? The books report minus 78 because it goes and picks up this hydrogen. So please understand, I want to clear one concept, that generation of LDA, generation of this salt, this is what? This is a salt. This salt is generated in minus 10 degrees centigrade. There is no need of, that's completely wrong information that LDA generates in minus 78. No, LDA is generated minus 10. In order to abstract this minus, this anion, right, this hydrogen, and creating this anion, which actually generates this lithium enolate, this happens in minus 78. So we need it. And in some cases, minus 78 is not required actually. Minus 40, minus 30 is fantastic. Okay. So this has to be cleared first. And then coming to something like competitive reactions, and we talk about kinetic and thermodynamic stability, we were we were discussing in the last class. And if we take that a compound like 2-methyl cyclohexanone and use an LDA, in one case you have a chances to generate a more thermodynamically controlled product. In one case we call it kinetically controlled product. And why does it happen? So why we call it a thermodynamic control and why we call it as kinetic control? Because this is a more thermodynamically stable product. Okay, and that we can do in different conditions. So this is how we explain the energy differences between a thermodynamic product and a kinetic product. And I'll just come to a beautiful example on this deuterocarmycin. If you see in this reaction, I write it in this way. A beautiful example of a kinetic and thermodynamic control, particularly in asymmetric reaction. You can see in this Dickman-like condensation, the most stable product was observed conducting the reaction under, please try to understand, conducting the reaction under equilibrating conditions for the reversible reaction, while the alternative kinetic product was observed when the reaction was conducted under lower temperature and non-equilibrating kinetic conditions. See, what is the difference? Please try to see this. This is very, very important. You have the same starting material, you use the same base, and I already showed you how LDA is generated. THF minus 78, 30 minutes. THF, same solvent, minus 78 to minus 40. And the right hand side we generate an APMR of the others. We change the chirality, we change the asymmetric induction. What change you find in the two different reaction conditions? This is very vital. I want to highlight you that how we are powerful, how we can control reactions. Okay, it's in our hands and here. How you are going to control it. See, same base, same starting material, same solvent, and we explain in one side a kinetic control and the other side a thermodynamic control. The kinetic control gives us 5 to 7.1 diastereomeric ratio, whereas the thermodynamic control gives you a single stereoisomer. What we do is creating a reversible and an irreversible condition. This is very, very necessary. Please try to understand. Very complex molecules, chiral centers, we just do an equilibration. How do we do the reaction? I told you that after generating the LDA at minus 10, we go down, we make it farther lower at minus 78 and add the starting material into the LDA. So it's a reverse addition. You generate LDA at minus 10, go below minus 78, then you add the starting material. And at minus 78, you rotate the reaction, or you keep the reaction stirring at 30 minutes, quench the reaction there itself. And in other condition, you add it and take it slowly, leave it, warm it to minus 40. It's a warming up, okay? And it comes to minus 40, and then you put water and quench the reaction. What you are doing? You are just equilibrating the conditions. So it's in your hand. And in the process, you see, you change the stereoselectivity. So every reaction, see, it's in our hands how we use our tools. Okay. So you make this an equilibrating reversible condition, and you make this non-equilibrating irreversible condition, and in the process you get a mixture of diastomers and kinetic control conditions, and in this case you get a thermodynamic control with a single stereoisomer. Beautiful example. I have not found such a beautiful example in such type of Dickman-like condensation, which clears our concept about kinetic and thermodynamic control. Okay, is that clear? Sorry, I don't know. Okay, why this is coming? Yeah, okay. Okay, so I think this is, we have discussed. So this is a Procal center. Yeah. Now, coming to the next part. So we discussed about FGs, functional groups, but just come to the point where I would like to highlight something. You all know what are this. I think you know this you are knowing from class 12 chemistry maybe. This is what is what? An aldehyde or a ketone, right? You have been writing it for long, and if you just use a protonation or an alkylation, you generate in the process like oxocarbenium ion, right? And then this is also known to you, depending on you have one hydrogen or both alkyl groups, and you can call them as an aldimine or ketimine. Basically they are imines. And the second one, you also generate or activate this imine with a proton with an alkyl, and you call it iminium ion, right? These are functional groups, most versatile sources of electrophilic carbon. So we need electrophilic carbon in synthesis and every type synthesis, everywhere we talk about this. But I would like to know you, which is more electrophilic? You tell me. Which is more electrophilic? Again your sense of toolbox comes in. Which is more electrophilic? Why it is necessary? Because you need to choose that what would be your starting material. Very simple question. These are 4 and all these have electrophilic carbons. What I want to mean. Aldehyde, ketone, oxocarbenium ion, aldimine, ketimine, iminium ion. I would like to ask, what about the polarization? Because we know we have been reading about this carbon positive and oxygen negative from our class 12 chemistry, and do we have a quantification where we would like to highlight that which one is the most electropositive one? What is your opinion on this? Which is going to be more electrophilic, most electrophilic? Okay, I give you a quantification. So this is what is a calculation and gives you the partial charges, okay, as familiar, as we know all these polar resonating structures, and we find some molecular orbital calculations, and they say that the delta positive in case of iminium is 0.33, and the delta positive in case of carbonyl is 0.51. For an iminium ion, it's 0.54, and for an oxycarbonium ion, it's 0.61 when R is H, and 0.63 and R equal to methyl. So now you tell me that why it is necessary. It is necessary because if you want to go for an electrophilic addition, a nucleophilic addition to a carbonyl, then this gives an idea that which one you should take. Because I have seen students coming to me and saying, sir, इसमें reaction बिठा रहे नहीं जा रहा है. You want to go for a nucleophilic addition to a carbonyl and the reaction is not going with a nucleophile. So what should you do? Will you go on repeating the reaction 100 times? No. In that case, these minor details are necessary for our reactions, and in the process we go towards asymmetric synthesis and catalysis, and this gives us a clear identification that if we want to have the best activated carbonyl, then as per this ab initio calculation, the oxocarbenium ion is the best one. So if you want to do a reaction and you want to add a nucleophile to an activated carbonyl, then this activation, this proton activation, which gives you the highest delta positive, is the best one. You should not choose an imine, or you should not choose an iminium ion. Rather, you should take the carbonyl and activate it like a proton activation. So the electrophilic potential of the C or a carbonyl functional group may be greatly increased by either Lewis acid coordination or protonation, and the magnitude of the increase is about 10 to the power plus 6. So we have been telling it. We have been telling it that we have been showing that Lewis acids been coordinating with carbonyl, but where is the quantification? So we need to know the quantification, we need to know the facts. The facts is this, that this is much more activated than an iminium one. Okay. So if you want to do a successful reaction, we want to do a successful nucleophilic addition to a carbonyl, the best way is you activate the carbonyl. This is the best one. Don't try with iminiums. Okay. There are other things of conditions as well when we feel that we want to go for nucleophilic additions to carbonyls. Why we are studying this? We are studying this because this is where we generate enormous number of asymmetric molecules. In this concept, we should also understand that if the nucleophile maintains an 107 degrees, or which we call it as Dunning-Burgi trajectory, this angle of attack has to be maintained as well. So the first thing is an activation, and the second thing is attacking of the nucleophile with the perfect trajectory is very important for such additions. So as a chemist, we should always remember these considerations, very, very important. Okay. Now comes to the next one. So what about C double bond O versus and C double bond OR plus? Any idea or any quantification on that? Yes, we understand. We understand that the LUMO coefficient, what we show in the slides on carbon for B, will be considerably larger than that of A. Does this mean that there is a lower constraint on the average of angle of attacking nucleophile? There is absolutely no experimental proof for this question, but it is worthy on consideration. I will also come to some others one by one, where you will find that there is a change on what concept we have already read through. Okay, I'll skip this and come to the final. Okay, this is, I think, one of the most fascinating understandings of of intermediates that we have been dealing in day-to-day life, particularly when we talk about C double bond O addition. See, simple reaction. If you take a carbonyl, for example, and formaldehyde, and have water in the system, you generate a coordinated transition state, and this can be a T1 and that can be a T2. This is what shown by Schoen in Jackson 1983, and he completely says with his theoretical consideration that we will have an intermediate where the carbonyl is actually attached to one molecule and gives a 4-membered transition state, whereas there can be a possibility which is of much lower energy and having a similar transition state or activation of the carbonyl with 2 molecules of water. So this is what was proposed in 1983, where he was discussing only a simple concept of carbonyl hydration, nothing else. But what was the impact? I'll show you. So just correlate this proton shuttle. Proton shuttle means you have a carbonyl, you have water, it attaches the carbonyl and releases back. And on the other side, we all know about Grignard and Barbier-Grignard reactions, where we think that the alkyl zinc or magnesiums attack in this carbonyl. And I will just highlight one important information, what the scientists have observed, that catalytic amounts of zinc iodide dramatically catalyze the addition process. As a student, we need to correlate these two observations. Very, very important. See, when we hydrate a carbonyl, we talk about two transition states. One is 4, one is 6. One involves one molecule, the other involves two molecules. When we come to Grignard and zinc addition reactions, we find that addition of zinc iodide, it's very easy, right? It's just attacking of or formation of an O zinc. So then why addition of zinc iodide catalyze the reaction? What is the implication? See, why this is necessary? Because carbonyls or addition of nucleophiles to carbonyls is the best used or best explored reactions in academia and industry for creating asymmetric synthesis. So although this information is very small, but what are its implications? The implications is that what we have been reading in case of carbonyl activation is not correct. The main reason is actually there is a formation of a 6-member transition state. It's not the way that we show RCO ... zinc. No, that's not the actual intermediate. If that was the intermediate, then addition of zinc iodide could not have dramatically increased the reaction rate. So that is why I asked this question, does these results relate to real reactions? What does it mean? I mean that whenever we have showed this zinc or magnesium catalyzed reactions, we write it in a very simple way. Carbonyl ... zinc, and there is a nucleophile which is attacking from the carbonyl and making the reaction. We have been reading it throughout, but actually if you see inside the reaction and understand it, it's just nothing. All this is actually going through, the carbonyl activation is actually going through a transition state where there is an involvement of two molecules of the activator. In case of water, and also in case of organometallics like zinc. So this is the actual bimetallic transition state or involving two molecules. I'll also tell you the story of the Grignard reaction. Okay, the same thing happens with boron and also aluminium. In all such cases, it's just 6-member intermediate. It's not the intermediate that we have been reporting. This is also proved. So we have proved these reactions, we have experimental proof, numerously reported that it's a 6-membered intermediate which is actually activating the carbonyls. Now, what is this reaction? This is a reaction that we have been reading from our class 10, I think. What is this? It's a Grignard reaction, right? So Grignard reaction is something like you add alkyl magnesium bromide to a carbonyl to have this COMgBr. We write this, right? We have written all throughout our lives that this is what is a Grignard reaction. You take magnesium, add alkyl iodide, and the reaction goes like this, and it forms ROMgBr, put water, and you then get the product and alcohol. We have been writing this. This is absolutely wrong. The actual thing is this. The actual thing is something which we have not encountered, not seen, but true, which is the Schlenk equilibrium. And this completely suggests that a reaction happens, or the Grignard reaction happens better in solvents like ethers. They don't happen well when you take the solvent as THF, tetrahydrofuran, which is also an cyclic ether. And it happens to be fantastic when you take diethyl ether. See, THF, cyclic ether, diethyl ether is an alkyl ether. But numerous examples where the reaction of the Grignard reaction has not worked at all, 0% yield in THF, whereas 90% yield in diethyl ether. why it's happening. It's happening because this one, what has been reported, is completely wrong. It's actually the Schlenk equilibrium, and it involves not one magnesium. It involves actually 2 units of magnesium, and it goes through a dynamic equilibrium like this, and here S is nothing but the solvent in which the reaction is happening. And as the diethyl ether is an aliphatic ether, it easily coordinates and gives a very good stabilization of this intermediate in Grignard reaction. Whereas when you take cyclic ethers, 6-membered, 5-membered ethers, this type of intermediates are not formed. And that's why, these Grignard reactions happen to be very well in diethyl ethers, but they fail in cyclic ethers. This is only explanation which we can give you when we think of this type of equilibrium, which is the actual transition state when we talk about these Grignard reactions. But you just remember that we have been always writing this reaction, putting a proton and then just cleaving the OMG bond and giving the alcohol as a product. Okay, so why this is necessary? This is necessary because we need to understand what type of intermediates are actually working. Otherwise, you cannot induce the chirality. To induce chirality, we need to understand what is the actual intermediate of the reaction. So there is a huge difference what has been proposed all the way along and what's actually happening through a Schlenk equilibrium in case of a Grignard reaction. Okay? Now, this is one thing, okay, I found this, that although there was a Schlenk equilibrium we have been proposing, where is the proof? And there is a proof. This was a report in JOC by 2002 by a Japanese group, Yamazaki, where actually he was successful to get the single crystal X-ray structure of this type of an intermediate. Beautiful work in JOC. He has actually seen that there is solvent coordination, and he has isolated this intermediate, and not even that, he has also solved the X-ray crystal structure in this paper, who has clearly proved that actually this is not the intermediate. This is actually the intermediate in a Grignard reaction. Okay? Fantastic. Okay. Now the last part, what I would like to highlight is coming to the original one, that when we create chiral centers, how well we are equipped with the knowledge of utilizing our toolbox. Okay. See, this is something which Dobbin reports in 1956 in JACS, and it says that if you have a simple molecule like 4-tertiary butyl cyclohexanone, and you want selectively one of the diastereomers, then actually you can choose your reagents. You see, he have given a fantastic graph, and he shows that when he uses diabal in this case, then actually the ratio of the actual diasterone isomer is 72, whereas if you use selectride as a reducing agent, it's completely reverses. Why this is important? See, there is no such group close to the carbonyl so that it can induce the attack. But actually you are choosing different reagents. So this study by Dobbin supports that you should not require anything closer to the prochiral group to control the stereoselectivity. That's not required. Okay. What is required is your actual knowledge of the toolbox, and which is reagent list. Because this clearly understands that when you take diabal, then the axial is 72, whereas equatorial is 28, and when you take selectride, it's just reverse. There's a huge differences. So this gives an idea that if you have a simple carbonyl and you want exactly the equatorial one as the major, I can choose the perfect reagent to do it. There is no need of something called the substrate control. That's not required. And there are numerous examples he has shown where there is complete reversal of stereoselectivity. Okay. So here comes, the way to understand that how we approach the product development and the steric approach control. Okay. So I stop it here, and although I have some more slides, but I will post you up. Let me come up with one small tutorial, because this is actually for the tutorials. I had many slides. So now, what type of product you can think of in this reaction? Can you just draw? Okay, I'll come to the product. So if you have a reaction like an LDA with an benzaldehyde, it actually forms a reaction the way I have shown. So you form an n-butyl lithium, you take n-butyl lithium and form an LDA and generate the enolet, and through all these steps you go up to the product. Okay. Now the second one is just a small base catalyzed reaction, and I want to know you what is the name of this reaction and what is the reactive intermediate involved in the reaction. What is the name of the reaction? Okay, so it's something like a Dickmann condensation, what we discussed regarding this, and the intermediate is an enolet. Okay, is that correct? Okay, very good. Now the third one is a reaction where we use a substrate which has two esters in both the sides, and we have a base called sodium methoxide and protonation, and which one is the correct product and why? Okay, anyone from this side? Which one is the correct product? So it's C. Okay, anyone from this side? Okay, let me see. So it's not C, it's actually B. Okay, and we do it in this way. Okay, got it? Fine. Okay, now the last one. So you have sodium methoxide and ethanol, and we think of a product like A. So what is the product A? Okay. Then we go for a second alkylation. Then we do a aqueous NOH and water or protonation, and then we heat it and we get a decarboxylation. I want you to predict which is A, which is B, which is C. Okay. So, okay, I don't know this. Oh, sorry. Yeah, okay. So we go for a first alkylation. We have ethyl butyl acetoacetate in 69 to 72%, and then we go for a second alkylation, and then we go for sodium hydroxide, hydroxylation, and finally decarboxylation. Okay. So this is just examples what we plan for examination tomorrow. So I think at the end we are conducting an examination. The examination will have multiple choice, and we'll do the grading and give you certificates on that. Okay. Okay, I stop it here. Thank you very much. And I think tomorrow we have Oliver's class in the first, and then I go for organocatalysis. Okay, thank you.
One